May I request K. Raghuram to join on the dais, please. So, Raj, may I request Dr. Tipanna to welcome today's speaker with a flower bouquet. Anand sir, welcome.
Thank you very much. Thank you.
We have dignitaries in the audience. Let me request Dr. Tipanna to welcome Mrs. Bhumkar with a flower bouquet. I request Dr. Tipanna to welcome Ms. Didi Kale with a flower bouquet. Color Society past President Shri P.B. Deshmukh. Color Society immediate past President Mr. Mukund Hulyalkar. Thank you, Dr. Tipanna. And now, may I request you to address the gathering?
Good evening to everyone. Distinguished Speaker, Shri ANAND KULKARNI, dignitary on the dais, my guru, Professor Didi Kale, Priya Madam, and invitees and friends. I welcome you all on the behalf of the Color Society Managing Committee. We organize this lecture every year on the 20th March on the birth anniversary of Shri C.J. Bhumkar. This year also we have organized this lecture, and Shri C.J. Bhumkar is a well-known personality in the field of coating industry. We all know the contributions toward our coating industry. He was a first generation entrepreneur. He started Saujanya Colors Private Limited, a pigment emulsion company manufacturing, and now the growth of the company is in parabolic. Every year we invite eminent speaker having expertise in the various fields in the coating technology, economy, finance, and management. This year we invited a well-known speaker in the field of corrosion protections, Shri ANAND KULKARNI, Director, Corrosion Control Service Private Limited, and also a trustee, NES, International Gateway India section. Corrosion is one of the biggest challenging subject in all time. We are losing huge wealth because of the corrosion every year. Lots of work has done on this subject. Lots of work has to be done. So to understand more about corrosion and its protection by cathodic electrolysis, today we are going to hear from Shri ANAND KULKARNI. I'm sure you'll be enjoying the same. I would like to thank Shri ANAND KULKARNI to accepting our invitation and coming all the way to deliver this lecture and enriching and enlightening us with a wide experience and knowledge. Coming to the Color Society and its activity, the Color Society is 55 years old organization founded by well-known personality like Professor N.R. Kamath, Shri Ravi Raghavan, Shri Bharatiya, and many more. Main objective of this organization was to spread scientific and technical knowledge related to paint and allied industry. Also, bringing the professionals from this area to the single platform. Color Society is in past led by well-known eminent people like Ashwin Dani, Dr. Saxena, Shri C.J. Bhumkar himself, Dr. Prasant Sawant, Dr. Manwar, and many more. The main activity of these Color Societies are, we organize endowment lectures. Beside Shri C.J. Bhumkar, we also organize Professor N.R. Kamath Memorial Lectures every year on the 5th September on his birth anniversary. We also organize periodically lectures given by the industrial people. We run a diploma course in paint technology. We organize international seminar every year. This year we have organized seminar in Faryaz Hotel Lonavala, which was very successful. The highlight of this seminar was Dr. Anil Kakodkar, ex-chairman Atomic Energy Council, was chief guest of the function. Mr. Subhas Dandekar, from the Kremlin, Mr. V.S. Bhakre were awarded Lifetime Achievement Award during this function. Mr. Rajendra Thakkar and Mr. Bharat Tavre were awarded the Fellow of the Color Society during this seminar. This year on Delhi chapter, we have organized one more seminar at Delhi. This seminar also went very successful. I would like to take this opportunity to thank Bhumkar Madam and his family for supporting time to time and also gracing this occasion by their presence. Once again, I would like to thank our today's speaker, Mr. ANAND KULKARNI. Thank you, sir. Thank you very much. Last but not least, I thank you all for coming and making the evening successful. I invite Shri Srikant Joshi to share his experience with Shri CJ Bhumkar. Thank you.
Thank you, Dr. Tipanna. Before handing over mic to Shri Srikant Joshi, I request Madam to come forward and say a few words. Priya ma'am.
Good evening, everyone. It's always special to be here in this august institution on this occasion. Thank you to the Color Society for keeping the memory of my father-in-law, CJ Bhumkar, alive every year, and for organizing this lecture. Mr. Bhumkar was a person, he was a people's person, and he was all about bringing people together, keeping people together. So indeed, this occasion is absolutely apt for him. It's all again about gathering people together, and and the other strength he had was on technical. So bringing people together for something about technical excellence. So this is there couldn't be a more fitting memory for him. So thank you, and we are looking forward to hearing you, Shri Anand, very, very excitedly, to the in-depth knowledge please share with us that you have in your subject. And thanks to the Color Society.
Thank you, ma'am. Now may I request Srikant Joshi ji to revive some of the memories of Sri CJ Bhumkar, because he worked with Bhumkar Sahab. I think there is one more person who worked with Bhumkar Sahab is Deshmukh Sahab. So I request Srikant Joshi to revive some memories. Srikant Joshi.
Good evening, everybody. Good evening. Just now you have seen, Priya Bhumkar said, it is the impact of CJ Bhumkar. The way she said. Somehow I remember Bhumkar was talking like this only. Then anyway, I will read out. First I will read out the biodata of his in simple language. And then I will do little extra, more. Biodata. Just I will read it, right? Mr. CJ Bhumkar, founder and chairman of Saujanya Color Private Limited. Completed his BSc Tech and MSc Tech from UDCT, earlier UDCT, now it is ICT. Mumbai, fellow of surface coating technology from UK. He was a member of American Chemical Society. He has worked with Asian Paints, the topmost paint company of India. For 20 years, he was technical manager and director of the company and was a member of the board of directors. In 1982, Mr. Bhumkar started Saujanya Enterprises as a proprietary company, morphed as Saujanya Color Private Limited in July 2008. Okay. This company is highly specialized in dispersion of pigments, producing unique products for the paint industries. The product manufactured by Saujanya are world-class and exported to 35 different countries in the world. Saujanya Color Private Limited Ltd is ISO 9000 certified company and rated highest performance company by CRISIL. Turnover is about 250 crores. If less, please excuse me. Okay. He held important positions in the industry associated like chairman, Indian Paint Association, Western region, that is this side of part of it. President of the Color Society, member of the Mining Committee of UDCT Almena Association. He was bestowed with Color Society Lifetime Achievement Award, Fellowship by PACT, and also Entrepreneur Award by Indian Achiever Forum. He is distinguished alumni of UDCT. He was a permanent invitee on the government body of Indian Paint Association. He was honorable editor, advisor of Paint India magazine for almost 40 years and has published more than 50 technical papers in various journals. He is listed in the directory of World's Who's Who. Mr. Bhumkar has chaired many sessions of the association like IPA, ISPA, Color Society, PAT, IRMA, and Printing Ink Manufacturing Association. His company, South Indian Color Limited, as a private limited, has installed awards like Gold Medal, HBTI, Kanpur, and also I-Star, Vallabhnagar, Gujarat, for the topmost rankers in the paint technology examination. Now, this is all about C.J. Bhumkar. Now, what I am telling you about our Bhumkar, we used to call him as Nana. It's our favorite. He interviewed me, that is why I was in Asian Paints. And what I seen in Bhumkar, that I will just read out. Actually, it is for the students. Most of the people know about him very well. But those who are students, you don't know who is Bhumkar. And we are all, only because of him, the impact what he has given, created on him. The way he was talking, the way he was walking, the way he was, everything was fantastic. Now, I will not take much of a time, because the time is definitely a constraint over here. I will read out. C.J. Bhumkar means what? C stands for commitment. That's one thing. J, Josh, dynamic. You see the dynamic of, if those who have seen dynamism of Bhumkar, they will really appreciate. They only know what is dynamism is C.J. Bhumkar. That's it. B, boldness. One time ago in Asian Paints, he was so bold, he told one of the persons, behave like a director and not like a manager. That is boldness he was having in Asian Paints. I am talking of humble. Such people are many times arrogant, but he was not. Absolutely humble person. Okay. Universal personality. You are seen in Who's Who. His name is there in Who's Who. So he's a universal personality. M, motivational manager, motivational management. Normally you cannot motivate. It's very difficult to motivate by the people. But if you are with him, you are motivated. It's like electric current. If you touch a person electrified, you will get current. The motivation is the bin-born quality of his. Karma yogi, always doing work. It is not only technical, it's gathering people, what she said rightly. People oriented, technical oriented, music oriented, and what so many things he was oriented like that. Acknowledgement. If you do something, many times say, Joshi, excellent, very good, nice, excellent. Or if there is no other, you will feel shy when you will say like that. That's the thing. And last, research mind. Research mind is very important. Come on, all these qualities are there in one person. So I would say, if you say Bhumkar is a management book. We need not refer any management book of any personality in the world if you know C.J. Bhumkar very well. Thank you very much.
Thank you, Srikanthji. And really is a great person. I had also had the opportunity to work with him or interact with him on various forums of the Color Society, IPA, as well as ISPA all together. So now may I request Mr. Raghuram to introduce today's speaker. So you can hand over directly. You can hand over directly to the audience.
Hello. Good evening, everybody. The senior stalwarts sitting across in the audience and the stalwarts here. There's a huge amount of resonance of Mr. CJB. I always call him CJB. Hail technology is his motto, but never forget, never forget, he's a great marketer. And he used to take people along. And before I go to introduce the speaker, I'd like to tell you why did we pick up this topic of presentation today. I'm not talking about the caption. We call it CP. CP is called cathodic protection. People in UICT or ICT today, we all talk about corrosion protection by using polymer, coating, paints, maybe thermoplastic, thermostatic, whatever. But there are situations when the paint and cathodic protection go together. Which supplements what is a $1 billion question. Supposing you ask a CP man, we say that, but for CP, paint will fail. And if you go to the other side, you say, but for paint, the CP will fail. But the reality is that there are situations when the cathodic protection will come to the rescue and protect. For example, let's say you have a frigate you have a vessel, you have an offshore platform, underneath you don't have a coating, you have pipelines, you have underground pipelines going on. Somebody did ask, and Anand KULKARNI said it is a cathodic protection for submerged pipelines and also above ground facility like piles. You have a pile and you have a situation where you have salinity, you have oxygen. So CP protects. You may not be in a position to do the coating at all. Maybe somebody will say, I'll go down, we'll have special coating developed which can cure underwater, fine. But if you have a platform, you will have a coating. But over and above that, you will have anti-fouling. And what is going to protect the offshore platform, which is maybe 30 years today, is basically cathodic protection. So with this small thing, the marketing, the cathodic protection for the paint people here or the polymer people, CP is where he was. Since 1970, I have been talking to his gurus like Purohit, Dr. Lotlika, so many people whom I met in Nozzle, and the concept of CP is one thing which has just gone into my blood. I thought I will have a speaker who will pass you, possibly pump in more information of interest to you and make this lecture wonderful. Mr. Anand KULKARNI is an electrical engineer and holds an MBA degree from University of Michigan, USA. As a Director of Corrosion Control Services, he is a Director of Corrosion Control Services and he is responsible for the execution of onshore and offshore projects related to cathodic protection. They call it a CP, for oils, gas, petrochemical and process industry. As far as 3 C's are concerned, that is Corrosion Control Services, CCS. CCS is a pioneer organization, used to work hand in gloves with Dorsal. And we are Dorsal were the only primary pipeline people in India who went abroad too. And there was a jodi between them and CCS. He is the pioneer and the gentleman is heading the CCS. So he has got 30 years of CP covers, a range of application including underground and offshore pipelines, plant piping, tank bottoms. I'll touch upon the tank bottom with your permission for a minute after I complete this. Tank bottoms, jetty piles and other buried and submerged sea structure, including CP surveys and specialized studies on AC and DC interference, detection and mitigation. Currently, Mr. Anand KULKARNI serves as the trustee of NACE, National Association of Corrosion Engineer, International Gateway India section, and is also a secretary of the East Asia and Pacific Rim Area Board of NACE International. He was a founding member of NIGIS when it was formed in 1992. A cathodic protection specialist certified by NACE International, Mr. Anand KULKARNI is a NACE accredited cathodic protection instructor as well. He serves as a member of Cathodic Protection Review Board and recently formed task group of corrosion management standards besides other CP related tasks and technology exchange groups of NACE International in keeping with his interest in education and teaching. He has authored technical papers and delivered talks related to CP for conferences on corrosion both in India and overseas. Coming to take back tank bottom, there is a virtual, this is a practical situation which I like to explain to understand the impact. If something is not protected, what happens? Tata, they have a tank farm. They have a tank farm. This tank farm, they store the material for themselves as a raw material, as well as they are also lending the tanks for somebody else. So CTTL was a tank farm in Bombay, besides the Tata Power Station. There were in the balance sheet, there was a loss of around 10 crores every year. Every year. The input, store it, the output, nothing could go wrong because the storage and selling, you are only selling services. I am storing your goods, so for servicing or lending. But believe me, it is found out that the tank bottom had corroded. All the tanks have started leaking. It took 3 years for them to identify what is the tremendous loss. The tank bottom had gone away and all the material cargo, we call it as a cargo, the cargo that is filled in is lost. So the revenue, that means the input, whatever as material is coming, when it came out, there's a huge amount of 30–40% loss because the tank could not hold the material. And the CP gave them results. Over to Anand to take over and explain further. Thank you, sir.
So Professor Mahanwar and Dr. Tippanna, Mr. Raghuraman, Mrs. Priya Bhumkar, distinguished invitees, ladies and gentlemen, good evening to all of you. I must at the outset say that I'm very privileged to have been invited here to deliver this C.J. Bhumkar Memorial Lecture, especially after I heard Priya talking about her father-in-law. I have had the privilege of meeting her, I think about a couple of years ago when she visited me at our office in Tardev. But we were talking about something else, and today she shared some of her memories about her dynamic father-in-law. And of course, Mr. Joshi, if I mistake not, talked about him in great detail, a very heartfelt tribute to Mr. Bhumkar. So I feel really privileged to be here, to be talking in memory of someone as great as Mr. Bhumkar. Today's topic that I've chosen, or rather the title that I've chosen, is because of a similarly great man. He is the founder of Cathodic Protection, and his name is Sir Humphrey Davy. And if you look at the slide, you can see that he lived in the 18th century and the earlier part of the 19th century. And it is this gentleman who is credited with coining the word electrochemistry. Sir Humphrey Davy was a man of ample means. He was knighted by Queen Victoria, he became a baronet, he was a president of the Royal Society. But one of his greatest discoveries, as we will see a little later when we come to the last slide, was his protege, the person whom he mentored, Mr. Michael Faraday, who went on to surpass Humphrey Davy in terms of his achievements in the field of physics and chemistry. And if you see on the right hand side of the slide, the words in italics, those are his words, and it refers to 1824, when the British naval ships were to be protected from corrosion. They were wooden ships, they had copper cladding, and the copper used to get fouled because of marine organisms, obviously. So Sir Humphrey Davy, who was a professor of chemistry at the Royal Institution, was requested to find a solution. And he found, as he has written, that a piece of zinc as large as a pea, or the point of a small iron nail, is adequate to preserve or protect 40 or 50 square inches of copper. So it is really this 1824 incident that is a precursor to what we call today as cathodic protection. This is something that we as students of chemistry in the 9th standard have been looking at, different metals. And the only reason I put it out here is to just refresh your minds, because when I teach, Raghu mentioned that I am an instructor for cathodic protection. These are certification courses. which are set by NACE International. And I like to refer to these things as ghosts of the past. So a lot of these things that we take for granted in school and we think we're never going to see them again often come to haunt us later. And if you look at this series, you can see that these metals out here are what are termed as the active metals. Active meaning they have a far greater propensity to interact with the environment. The metals at the bottom are noble relatively, which means that they don't interact as easily. So it is really this difference in metal constitution, metal electrochemistry, metal electrochemical potentials that sets the stage for corrosion and cathodic protection. So this is just a little bit of a primer about cathodic protection. What do we mean by a corrosion cell? And when we talk about corrosion cell, I must also clarify that when we talk of cathodic protection, it refers to protecting metals in soils or in water. So we are not talking about atmospheric corrosion at all. That part is taken care of by the paints and the coatings. So this is something that is used or applied only for buried and submerged metallic structures. So what we need for a corrosion cell is what is called as an anode, a cathode, a conductive path between the two, and an electrolyte. So just look at the schematic, and I don't want to spend too much time on the technical parts, but it's hard to get away from explaining these when you're trying to talk about cathodic protection. This shows an iron sheet as well as a zinc sheet. Iron is called as a cathode, zinc is the anode. And this is an electrolyte. It could be water, plain tap water, it could be salt water. And we find that when we connect electrically with a simple copper wire two dissimilar metals, then we have an exchange of current. And why does this current get exchanged? It gets exchanged because one of the metals is more active compared to the other. In this case, it's zinc, and we find that zinc dissociates. We call this as the anodic reaction into a cation and electrons, and these electrons in turn are available for the corresponding reduction reaction at the cathode, where oxygen gets reduced to give you hydroxyl radicals. So really here it is the corrosion of the more active metal that sets up a current in the circuit. So we have zinc corroding, and zinc corrodes preferentially, which is why this cell is also called as a sacrificial cell, because zinc sacrifices itself when it is connected to a more noble metal, iron, and while doing that, the corrosion of zinc sets up a current in the circuit, and you find that the current, of course, is from the zinc anode to the iron cathode in the electrolyte, and from the iron cathode to the zinc anode in the electrical circuit. The electrons, of course, flow the other way. I don't want to get into details of all that. Most of you probably already know this. The battery cell is probably the only place where we find this corrosion helping us or serving us. When we talk of corrosion, it obviously has a negative connotation. So we're trying to protect things from corrosion. We want corrosion control. We want anti-corrosion, anti-corrosive coatings and so on. But this is probably the only case where we use corrosion for our benefit. So we have a simple battery cell. This rod that you see here is carbon. The case is zinc. They are two dissimilar metals with different electrochemical potentials. And because of the natural difference in potentials between these two, we have 1.5 volts available to us as power. And we routinely use this in devices such as this or any other appliance. Here is an interesting example to show how corrosion affects pipelines in this case. So we obviously know that when we have dissimilar metals, there is the risk of corrosion because they are likely to have different natural potentials. And when you have a difference in potentials, you have the possibility of a corrosion cell in the presence of an electrolyte. But also, in addition to dissimilar metals, we can have dissimilar conditions of the electrolyte. And this is really what happens out on the field when we talk about pipes, or we talk about tank bottoms, we talk about plant utilities that are buried. Here you see a section of a pipeline, and you can see that there are two types of soils, soil type A, soil type B. And if you have differing soils, the heterogeneity of the soil creates conditions for differences in potentials on the same pipe. As a result of which we have one area which is relatively cathodic to the other, one area which is anodic. The anode obviously corrodes. As you can see here, one more issue that I would like to emphasize is that this oxidation reaction is basically what is corrosion. And at the cathode, at the iron sheet, we find that there is no corrosion because whatever electrons are needed for reduction of oxygen, which is a natural phenomenon, are supplied by zinc. So as long as you find that you have electrons being supplied from an external source for a metal, then that metal is going to get protected. And that is why at the cathode you have what is called cathodic protection. When you find that a metal has become a cathode, it is automatically protected because it does not corrode. So when it doesn't corrode, the other term to be used is it is protected. Here is another example similar to the soil that we were talking about. You have a pipeline going under the road, and we find that under the road you have this area which is under the pavement, which is low in oxygen content. The section of the pipe on either side of the road is exposed to a perennial source of high oxygen because this is soil. So we find that if you have a situation such as this, the section of the pipe under the paved road is going to become anodic compared to the other two areas, and so you would have this area corroding and this area getting protected because the low oxygen impels electrons to flow towards the cathode for the reduction reactions. And we find that oxygen being a cathodic reactant, wherever you have high oxygen content, that area becomes the cathode. So this is a galvanic cell, and the galvanic cell is obviously the result of a difference in potential, a natural difference in potentials. And so we find that the natural difference in potentials is attributed to having dissimilar metals or dissimilar conditions surrounding the same metal, which is what we've just seen. Apart from a galvanic cell, we have something called as an electrolytic corrosion cell. In the galvanic cell, we find that the corrosion of the more active metal sets up a current in the circuit. This is the exact reverse. In the electrolytic cell, it is the current which is forced into or out of a material that causes corrosion. So the electrolytic cell is an example is a stray or interference current, which we will touch upon briefly a little later in the lecture. But it is important to know that the source of power in this case that causes current is external to the anode and the cathode. In the first case, which we saw some time back, the galvanic cell, you can see that there is no external source of power. How does this power happen? The power is the result of the natural difference in potential between these two dissimilar metals. But in the case of an electrolytic cell, look at this slide. So you have a DC source like a battery, maybe a 9-volt battery, and you have two sheets of iron, the same metal, and you connect the positive of the DC battery to one, the negative to the other. And now what you've done really is you're polarizing one sheet positively, you're polarizing the other sheet negatively. You're forcing current out through this iron sheet, and because you force it out, this is going to corrode. So we find that whenever you see current leaving a metal and entering the surrounding electrolyte, that metal is going to corrode. It's called an anode. And whenever you have a metal which seems to receive current from the electrolyte, it gets protected, or rather doesn't corrode. It is preserved, which is the word that Sir Humphrey Davy used in our first slide. So when Humphrey Davy actually looked at protecting the copper-clad ships, he realized that zinc ingots, and if you had sufficient number of zinc ingots which were placed on the copper cladding, it was able to protect the copper of the warships. And so this is the genesis of the definition of cathodic protection, technique to control the corrosion of metal surface by making the surface the cathode of an electrochemical cell. Remember, when we say an electrochemical cell, we're looking at a cathode and an anode. We're looking at a metallic conductive path between the two, and we're looking at a surrounding electrolyte. So both the anode and the cathode sit in a common electrolyte. That's important. So you need all these four elements. This is the NACE Standard Practice 0169 standard definition of cathodic protection. This is a more technically accurate definition, which simply says that if you're able to polarize all the cathodic sites, because when you look at a structure like a pipeline, it is the same metal. So what is it that causes cathodes and anodes on the same metal? We already saw some time back a differential cell schematic where we saw that when the soil is non-homogeneous, it may be different resistivities, it may be different salts in the soil, it may be different chemistry, different pH. The result of this heterogeneity of the soil causes a difference in potentials along the pipeline. So if you have a pipeline that is coated, and all pipelines today are coated, we have excellent coatings. We have fusion bonded epoxy, we have 3-layer polyethylene, extremely high electrical resistance, high dielectric coatings, which form a fantastic primary barrier to corrosion. But in and of themselves, they are not sufficient to prevent corrosion, simply because the better the quality of the coating, the greater is the risk of corrosion. Mr. Raghuraman was talking earlier about the fact whether you want CP or whether you want coatings. Really, they are both complementary. You need coating, obviously, and you need CP because you don't need a lot of CP, but you need a little CP to ensure that those small, tiny defects in the coating, whether it is 1 square millimeter or 1/10 of a square millimeter or 1/100th of a square millimeter, the smaller the defect in the coating, the greater the risk, exponentially greater the risk of corrosion. So we don't need much CP today, but if you didn't have CP, we are definitely going to have failures. So it's an absolute essential requirement, and which is why the Oil and Inspection Safety Directorate, or PNGRB in India, have mandated that all oil and gas pipelines and all assets dealing with oil, gas and petrochemicals need to be cathodically protected. So anyway, coming back to polarization, if we polarize meaning shift the potential of all the cathodic sites so that it equals the open circuit potential of the most active, electrochemically active anodic site. Well, obviously, if you have no potential difference between the cathodes and the anodes, then you don't have a cathode, nor do you have an anode. So then you have protection. And this is exactly what cathodic protection does. This is a schematic for a galvanic cathodic protection system. You use the word galvanic when we rely only on metals, differences in metals to provide power. That is when we use the term galvanic. We also call this sacrificial. As I said earlier, this anode sacrifices itself to protect the steel pipeline. So again, this is the same as the first galvanic cell that we saw. It's just that it looks different because we now have a real life example of a steel pipeline and an anode, and we have an electrical connection between them through a junction box or a test point. And we find that when we connect a galvanic anode, which is typically zinc or magnesium, we have the current being discharged from the anode into the surrounding soil, picked up by the pipeline, and returning to its source. So you have the galvanic anode getting consumed steadily, and the pipeline is protected. So the applications of galvanic anodes, if you look at all the applications, you will see that there are limitations, constraints. So we have short pipeline lengths, small surface areas, low soil resistivities. So there's a lot of constraints. You can use galvanic or sacrificial cathodic protection only for certain applications. I have a couple of slides up here to talk about the galvanic anode. So, zinc is of course the historically famous cathodic protection anode. As I talked about earlier, Sir Humphrey Davy used zinc ingots to protect the copper clad ships. Its potential to what is called a copper sulfate electrode, which is a reference electrode, I will talk about it in a bit more detail a little later, is minus 1.1 volts, and its rate of consumption is 11.8 kilograms per ampere year, which means that if you have 1 ampere of current being discharged from a zinc plate or a zinc structure for 1 year, then 11.8 kilograms of zinc would get consumed. So, zinc has been widely used for marine application, protection of ships, jetty piers, jacket platforms, until they discovered that there is a better metal, which is aluminium, and we'll come to that in a bit. So, zinc is a great electrode for both onshore and offshore applications. For onshore applications, there is a constraint in terms of soil resistivity. So, if you have soil resistivities which are relatively high, higher than say 25 ohm meters, then zinc doesn't act as efficiently as it would otherwise. Also, if you have chlorides or rather if you have carbonates or bicarbonates or nitrates, then we find that the efficiency of zinc goes down. It becomes, its potential shifts to the noble side. It doesn't really act as an anode. The other interesting thing about zinc is zinc needs to be extremely pure. So, we're talking about a 99.99% pure zinc for it to act effectively as an anode. Because for it to act effectively, it has to have a sufficiently electronegative potential. It has to be sufficiently active. We saw in the first EMF series slide that the more electronegative a metal, the more active it is. So, in order that it displays or exhibits this kind of potential, it has to be very pure. Then we come to magnesium. We find that magnesium is far more versatile than zinc because of its electrochemical potential. This is a mistake here, I am sorry. This should be minus 1.5 volts. So, it is more electronegative compared to zinc, and so obviously the constraint of low soil resistivity is taken care of. Magnesium is another great anode when it comes to all types of soil resistivity. So, it is the most frequently used anode for galvanic protection of steel structures, buried steel structures. If you have chlorides in the environment, it doesn't act like an anode anymore, so you don't use it for marine applications. And its rate of consumption, this is again wrong, this has got wrongly added because this is the aluminium thing, but anyway, the rate of consumption is about 8 kilograms per ampere year. So, that is again lower than zinc. This is an aluminium bracelet anode, and as the word suggests, it is used for subsea pipelines. So, when you have a subsea pipeline which is going to be laid on the bed, it is typically not only coated with some kind of protective corrosion barrier coating, but it also has a cement coating, and parts of the pipeline are left uncoated with cement so that this anode, aluminium anode, can be fitted on it. Aluminium is the most efficient anode for marine applications simply because its rate of consumption is very low. Zinc, if you remember, was 11.1 kilograms. This is only 3.1. It's a no-brainer. So, aluminium is far more actively used than zinc for marine applications. Its potential is similar to zinc, minus 1.1. This is a picture of a offshore platform with aluminium anodes on it, and all these white things that you can see, these are aluminium anodes. Now, this is a slide on reference electrode. You are trying to protect a structure cathodically. You want to make it the cathode of an electrochemical cell. You do that, but how do you know that it is adequately protected? And in order for you to understand, you have to look at the potential of the structure with respect to the electrolyte it is in. And to measure this potential of the structure with respect to the electrolyte, you use what is called as a reference electrode. And there's a variety of reference electrodes. Typically for all soil applications, we use what is called as a copper sulfate reference electrode. For marine applications, we use a silver chloride. This is a type of an electrode used on ship hulls. This is for internal protection. This is a slide on, I've focused on pipe to soil potentials because it's easier to explain potentials when you come to buried steel structures. These are pipe to soil potentials, and I want to show you how you actually take this measurement. This is a pipeline. This is the reference electrode. You connect the reference electrode, and as we saw earlier, it's a copper sulfate. You connect it to a high impedance voltmeter, and the positive terminal, these are direct current measurements, DC measurements. So the positive terminal is connected to the pipe, the negative to the voltmeter, so that you can get the pipe to soil potential with reference to the electrode. If you swap the polarities, that is, if you connect the negative to the pipe and the positive to the reference electrode, which would actually be the right, technically correct way of making the measurement, then you would get a positive measurement, which would mean it is the potential of the reference electrode with respect to the pipe. But for field use, it's common practice to use this copper sulfate electrode. You connect the negative terminal to the copper sulfate. And as you can see here, this depicts the pipe which is receiving current, so it is cathodically protected. And we find that we get a measure of minus 850 millivolts with respect to this reference electrode. You can see this picture here where you find that the pipe is not receiving current, it's actually discharging current, it's corroding. So if you find that the pipe is corroding, you find that the potential that it exhibits is obviously not as electronegative as when it is receiving current. Similarly, we find in this slide, although this is more for instruction, but it's interesting, when you place a reference electrode directly over the structure, you get a certain potential. When you move laterally away, you actually measure a greater potential because you have a higher resistive drop in the soil, right? Because every soil has resistance, the coating has resistance, and you have current in the circuit. So you have current times resistance, which is a IR or a voltage drop. So this is a slide for an impressed current CP system. This is an external DC power source, transformer rectifier, and these are what are called as impressed current anodes. The impressed current anodes are intrinsically different from the galvanic anodes that we saw earlier. So we talked about magnesium and zinc and aluminium, but these impressed current anodes are quite different. They're typically made of inert materials, materials which do not get consumed easily. And we find that these anodes are connected to the positive terminal of the TR, the negative is connected to the pipe. This is a reference electrode for monitoring of the potentials. And this is a schematic which is easier to understand. So you have a pipeline, we have a transformer rectifier, and what you have now set up is an electrolytic cell. So we are going to force current out through these anodes which are buried in the soil. This current that is discharged by the anodes is picked up by the pipeline. The reference electrodes provide information regarding the level of potentials or the adequacy of cathodic protection. And so you can have transformer rectifiers which work on an automatic feedback feature. So if you have inadequate potentials, you can adjust automatically the transformer rectifier output to ensure that the output is increased or decreased as the case may be, so that the pipeline is adequately protected. So impressed current CP, of course, does away with all the limitations that are imposed by the galvanic system. The galvanic system has very limited power because the power of the galvanic system is the result of the natural difference in the intrinsic potentials of two different metals. That's it. So obviously you have limited power. We looked at the electrochemical potentials of zinc and aluminium, 1.1, 1.5. You have very limited power available to provide protection. So if you have very high resistivities, if you have long design lives, if you have a 200-kilometer long pipeline, it's just not feasible to use galvanic protection. So that is when we use impressed current CP. Of course, you need an external power, an alternating current supply. Current output is variable. The electrolyte resistivity is not a constraint anymore, suitable for longer design lives. Obviously, because of the complexity of the circuit, you need monitoring and maintenance. And this last point is the most important, because once you have a impressed current system in place, interference with other structures has to be considered and dealt with. So the applications flow from the features. Now you don't have the constraint anymore. Large areas can be protected. Design life can be more. So typically you use galvanic systems for the construction phase of a pipeline. So a pipeline takes 1 or 2 years to build. You use galvanic anodes for protecting the pipeline, and once it's completely built and commissioned, all the mechanical activities are completed, then an impressed current CP system comes into play, and that can be designed for 20, 25, 30, 35 years as the case may be. So you don't have any constraint with the resistivities. Design lives are large. You can protect all types of structures, cross-country pipelines, plant utilities, tank bottoms, vessels, offshore structures such as jetty piles, platforms. Couple of slides on the types of anodes available. So this is what's called a high silicon cast iron anode. Basically it's iron. It has a certain element of silicon in it so as to reduce the rate of consumption. We know that the rate of consumption of steel or iron is about 9.1 kilograms per ampere year. By using 14 to 15% of silicon, we're able to reduce the rate of consumption to about 0.2 kilograms per ampere year. So this is a traditional impressed current anode used for the longest time through the 60s, 70s and 80s. And it was in the 90s that they started the use of mixed metal oxide coated titanium anodes. This is just a blend of rare earth oxides that is thermally applied to a titanium substrate, very low consumption rates, 1 milligram, 2 milligrams, 3 milligrams per ampere year. The different kind of configurations available for pipelines, for tank bottom. This is a great for a tank bottom. So what are the objectives of a CP system? We've already seen that a CP system is supposed to create an electrochemical cell, and it is going to turn the structure into the cathode of that electrochemical cell. And when you say that you're going to turn the structure into a cathode, you expect the cathode to receive adequate amount of current from the electrolyte, because only when it receives adequate current is it going to get polarized sufficiently so that there is cathodic protection. So that's the first important requirement. Second is to ensure suitable distribution of the current. So it's not sufficient just to have a source of power that is giving you direct current. You need to ensure that the entire structure is able to receive that current. So if you have a pipeline, you need multiple CP stations at regular intervals. If you have a plant piping, the problem becomes complex, because now you have not a linear cathode, but you have a network, because the piping could be spread all over the plant and it doesn't follow a linear route at all. So distribution of current, location of the anodes becomes very important. The anode system is very important. So there are two types of anode systems, remote beds and closed beds. I don't want to go into too much technical detail because it can get a little hairy and we don't have sufficient time for that, nor is that the objective of this lecture. But just to touch upon the type of anodes, a remote anode simply means that the anode system is physically and electrically remote from the structure. So what this means is that the pipeline, suppose that is the structure that you're trying to protect, is made sufficiently negative with respect to remote earth. And remote earth, of course, is the general mass of the earth which acts like an infinite conductor, which is at zero potential. So you have sufficient distance or spacing between the anode system and the structure or the pipeline, so that long lengths, long spans of pipeline can be protected using a single anode bed. So if you look at our modern day polyethylene pipelines, you could arguably protect with a single CP station and a single anode bed up to 70 or 80 kilometers of pipeline. Next is, of course, to provide adequate monitoring facilities, because monitoring is at the heart of sustaining the CP. So you need to make sure that the structure, the acid that you've protected cathodically is able to exhibit the electrical parameters necessary to ensure adequate CP. And finally, of course, to ensure minimal interference to other structures in the vicinity. These are the criteria of protection. Don't want to go into great details, but this is a kind of a magic number. Green because it's protected, minus 850 millivolts. This is for an onshore pipeline, NACE standard 169 of 2013. And it says if you have a structure to electrolyte potential of minus 850 or more negative is measured with respect to a copper sulfate reference electrode, and if this potential is a polarized potential, polarized meaning that this potential is basically measured when there is no current in the circuit. So you have to, polarized potential is measured upon interruption of all current sources. Basically, we want to ensure that the potential reflects the true polarization. When the current is applied, you have IR drops or voltage drops in the circuit, and they are of course not a measure of polarization. You want to remove those from the measurement. So you temporarily interrupt all current sources and measure what is called the off potential. And so this is the threshold of protection. Another criterion which is a direct measure of the cathodic protection is the 100 millivolt of cathodic polarization. So if we have a certain basic potential and we are able to polarize the structure negatively by at least 100 millivolts, and so we have a natural potential of say minus 600 millivolts. We polarize it and I get an off potential of minus 700 millivolts. And if my structure is not very well coated, it is, say it's a poor coating or it's a bare structure, then I can be safely assured that it is cathodically polarized because there is at least 100 millivolts of cathodic polarization. In the ISO standards 15589, there are additional criteria which address the problem of resistivities. We must understand that as resistivities change, the chemistry of the soil changes. And cathodic protection, as we've seen, is making the structure the cathode of a cell. It relies on primarily the reduction reaction in which we have hydroxyl ions being produced. Obviously, when we have hydroxyl ions being produced, the pH of the electrolyte is going to increase. So cathodic protection is exemplified by not just a shift in potential, but also by an increase in the pH. They are concomitant phenomena. You have an electronegative shift in potentials as well as an increase in the pH. So if you have high soil resistivities, then if you look at the old Porbet diagram for iron, we can find that even at potentials higher than minus 850, say minus 750, minus 650, we are able to protect iron. So this is exactly what the ISO standard mentions. And this is the criterion for marine corrosion, structure to water potential of minus 800 millivolts. I'd like to add here that these criteria of minus 850, they are not theoretical criteria, because as Humphrey Davy said, it's an obscure branch. It was an obscure branch, and it continues to remain rather obscure because it is very difficult to explain cathodic protection with mathematical models even today. It's not terribly deterministic. It's not like electronics. And that's obvious because it's a hybrid circuit, as you've seen. It's an electrochemical circuit. Part of the circuit is electrical. The other half of the circuit is either soil or water, which is a dynamic medium. Well, this is something that I put in because you're all paint and coatings people, so I thought it would be nice to look at how CP and coatings interact. So if you have a bare pipeline, and as a CP practitioner, I'd like to say this with some amount of pride, that if there's no coating on a pipeline, you can protect it cathodically. You don't need a coating. except that it's just too much current, it doesn't make sense. So if you have a coated pipe, it reduces the proportion of exposed metal, obviously lowers the CP current demand, and obviously the better the coating, the lower is your CP current requirement. Just look at this example here. You have a 30-inch dia, 10-kilometer long pipeline with different coatings, and look at how the current requirement, this is the CP, cathodic protection current requirement. So look at how it changes. For a bare line, say 240 amperes, which is a little on the higher side. Coal tar enamel, old 6 amps, coal tar enamel new 3 amps, a polyethylene coated pipe 600 milliamps or 0.6 amps, so that's really low. This slide talks about soil resistivity and CP. So generally speaking, when we have high soil resistivity, the corrosivity starts decreasing. This talks about span of protection for different coatings. So just look at, imagine one CP station comprising one transformer rectifier, one anode bed, and the structure. And the structure is a long pipeline. So we have multiple number of such cathodic protection stations along the pipeline. So if you have a coal tar enamel coated pipe, you could protect 37 kilometers, with a fusion bonded epoxy 65 kilometers, with a polyethylene 71 kilometers. So you can see that better coatings obviously reduce the CP current demand. This is the topic of some interest of late in cathodic protection, electric interference. And the reason for electric interference being a significant topic today is that cathodic protection is an electrochemical circuit, as you know. And this electrochemical circuit obviously creates an electrical field. When you have an anode discharging current into the electrolyte, whether it be soil or water, it's going to create an electrical field of a certain strength. And that electrical field will diminish in intensity as you move away from the source of that field, which is the anode. So if you have other neighboring structures with their own CP systems, or if it's welding, or if it's some other structure, it can cause a change in the electrical field, and that would obviously interfere electrically with the CP system. So the different types of interferences. DC rail traction have been a source of great problems historically in Bombay, especially when all our local trains used to run on DC, because the tracks actually were the return path for the current, and because the tracks were not isolated adequately from the earth or the ground, you had sufficient current leaking out into the earth, and if such current found a steel pipeline in its vicinity, it would just use the steel pipeline as an alternative route, because the current follows its own principles. It follows the path of least resistance. And so that was a source of great problems for a lot of pipelines through the 60s, 70s. My father, Mr. Kulkarni, is here, and he's worked on those pipelines at that time. Today, of course, all those lines have got electrified to AC, and we have a very small section of DC still remaining. I'd like to focus on the next slide, which talks about something even more menacing, which is the AC interference. In early times, there was no problem of AC because we had relatively poorly coated pipelines, coal tar coated pipelines. Their electrical resistance was low, so obviously their isolation from the ground, their electrical isolation was that relatively lower. And so we didn't see very harmful AC potentials on pipes. Today, with high electrical resistance coatings such as polyethylene or fusion bonded epoxy, we find very high alternating current interference. We find very high AC potentials on pipelines. And the reason for that is simple. A polyethylene coated pipeline has a very high electrical resistance, maybe of the order of 300,000 to 500,000 ohm meter square. And because of this high degree of isolation between the pipe and the earth, obviously the induction, because of AC, electrical induction, is very high. AC density on the pipeline greater than 100 amps per meter square, the corrosion is very likely. So you have NACE SP177 talking about 15 volt AC as the threshold for safety. You cannot have a higher voltage than 15 volts. And that really, if you interpret it in another way, if you look at a human body, 1000 ohm is my resistance. And if there is more current passing through me as a result of AC induction than 15 milliamperes, then it could lead to ventricular defibrillation, and that could lead to heart attack. And which is why you have 15 volt designated as the threshold of safety per NACE SP 177. But if you have high AC, the threshold for AC corrosion, this is the safety threshold. In case of a 1 centimeter square holiday in a 2500 ohm centimeter soil is just 9.8 volt AC. So today we have the specter of AC corrosion, which has created a serious problem in pipelines all over the world, because we find pipelines not only have high quality coatings, but they also run parallel to high voltage AC overhead lines, and that causes a lot of AC interference. So the type of coating influences the level of AC interference in a very significant way. A slide on corrosion in seawater. Seawater is about 20 ohm centimeters, very small resistivity, aggressive medium, high pH, and so depending upon the amount of dissolved oxygen and depending on where the structure is, you're going to have to design the CP system. In the case of seawater, as opposed to on land, we can use small voltages in terms of the DC power units to provide large amounts of current, because we have very, very low resistivity. So we have high corrosion, but the ease with which we can apply current is much better. So we have typically TR units of 25 volts and 500 amps, say for marine corrosion cathodic protection. On land, we have 25 volts, 25 amps, because you need far more greater voltage because you have higher resistances on land. And with that, I come to the last slide, and it's like coming a full circle. We looked at Humphrey Davy in the first slide, and this is his able protege, Michael Faraday, who at the age of 13 worked in a bookbinder's shop. He came from very humble beginnings. Obviously, he was working in a bookbinder's shop, so you can imagine, but he had a great interest in science. And Mr. Rebo, who owned the bookbinding business, was kind enough to set aside space for him to conduct experiments. And so Michael Faraday was busy reading scientific journals, the books that he bound, and he used to conduct these experiments. He was afforded the chance to attend 4 lectures by Sir Humphrey Davy, which he obviously was delighted to attend, and he took copious notes of Sir Humphrey Davy's 4 lectures on 4 days. He made a book out of those notes, bound it in leather, and presented it to Humphrey Davy with a request that he be allowed to work with him, to assist him. Well, Humphrey Davy said, I already have a lab assistant right now, so he said, I'm sorry, I don't have a vacancy. A month later, as they say, fortune favors the brave and the curious. The apparatus, the guy who was taking care of the apparatus in the lab, he caused a minor explosion. Humphrey Davy was livid. He kicked him out and gave a job to Michael Faraday in 1813 as an apparatus cleaner. So this young boy joined him as an apparatus cleaner. He went on to surpass Davy because he not only built on the foundation that Davy provided him, he actually is responsible for the laws of electrolysis, as we know. He also discovered the laws of electromagnetism. And he's the only scientist in the world to be credited with 2 units. One is the farad, which is the unit of capacitance, and second is the Faraday's constant, which is 96,500 coulombs per equivalent of weight of the material transferred in electrical charge transfer reactions. So this is Michael Faraday, a stark contrast to his mentor. The mentor was an aristocrat, belonged to the peerage. This guy came from humble beginnings. He twice turned down offers from the Queen to become president of the Royal Society. He turned down an offer of knighthood. He said, I want to remain plain, simple Michael Faraday. He turned down an offer from Queen Victoria to be buried alongside Sir Isaac Newton at Westminster Abbey. He said, I want to be buried in a simple place with a gravestone that reads, Michael Faraday, born so-and-so, died so-and-so. So a man of immense humility and truly a father of modern electrochemistry and cathodic protection. Thank you.
Thank you, Mr. Kulkarni. Any questions?
Hello. Excuse me. It was a very lively lecture, but I've been teaching this electrochemistry for some diploma students, and I'm teaching, in fact, in marine coatings. So I was going through a chapter on the electrochemicals. See, this is cathodic protection. There's one thing which I did not understand is that during the cathodic protection, when the electrons are traveling from anode to cathode, and that cathode is surrounded by the electrons, there is a polarization. And due to this polarization, every time there is a danger that it will be totally covered with oxides. And whatever coating system we are applied to that, delaminates because of the oxide formulation. So could you throw some light on that, please?
Absolutely. Polarization is an interesting phenomenon. If you look at the circuit, it's an electrochemical circuit. So you have electrons, as you just now said, in the electrical part of the circuit. But in the electrolytic circuit, in the electrolyte, it is the ions which are taking care of the charge transfer. And because of the huge difference in the type of charges, ions in the electrolyte, electrons in the electrical circuit, that you have this phenomenon of polarization. So what this polarization is doing, as you said, the electrons come to the cathode for the reduction reactions, and you have the hydroxyl formation and you have the oxide formation. In fact, whenever you have, if you're talking about marine corrosion and you have calcareous deposits or oxide layers, in fact, that inhibits corrosion. In case of onshore corrosion, it is really not so much the case because we have excellent coatings, and the type of defects that we see in modern day pipelines are extremely few and far between. So we are looking at currents in the range of milliamps, sometimes even microamperes, because you don't need that much current. So this issue of oxide formation, I haven't seen it to be a problem for the onshore at all.
So in that book it is given that actually a hydroxide formation is there, and when you use a primer like gas primer like zinc tetroxide, chromate primer, or subsequent barrier coat and finish coat, due to the hydroxide formulation, the entire system of the paint delaminates. That is why you have to take the care.
This reminds me of, and just give me a moment because this is a very interesting question. There was a similar issue on pipelines, not of delamination, but of what was called as disbonding of the coating. You're talking about disbonding of the coating. And this is a wonderful question too, because let us try and understand what happens in cathodic protection. As we already know, it's because of reduction reaction that you're able to protect the cathode. And when we talk of reduction, we're talking of a preponderance of hydroxyl ions. So yes, if you have too many hydroxyl ions, it is possible for the polar bonds to become weak and therefore for any coating to delaminate. But the fact is this, when we look at, and I have experience of pipeline, so I will speak about it from the pipeline perspective. There has been not a single incident in pipeline CP history where we find such disbondment of the coating near anode ground bits, because that is where we have the most electronegative potential of the pipe. So ideally speaking, it should be near the anode ground beds that we find this whole scale kind of removal of the coating because of loss of adhesion. But it's never been found near anode ground beds. In fact, it appears to me that this is caused because of the poor lack of adhesion between the coating and the substrate in the first place. In fact, if you have cathodic protection causing delamination or disbondment of the coating, it is because there is, it tells you places where the coating has not been bonded properly in the first place. Otherwise, there's no reason why cathodic protection would cause this wholesale kind of delamination or because we've never seen it in pipelines. And in pipelines, it is the area near the anode bed which has the most electronegative potential. So ideally, if that is a problem, if this hydroxyl ion is a problem, it should cause this kind of delamination. It is true that if you have excessive hydroxyl ions, they can obviously lift up the coating. But the reason they do that is there is probably not proper adhesion. The adhesion there is subpar in the first place. This is what I find in terms of pipelines, that when the coating is not properly bonded to the substrate in the first place, obviously you find it in only those locations. And this has been proved by tests in all pipeline CP history. And I have documented proof about this. But I'm not sure about other structures. I know about pipelines.
Thank you for that wonderful lecture. My question is about the open circuit potential, the OCP. You just touched upon it very briefly, but is that something you need to take? I guess you do have to take that into account when you design a system, right? Doesn't it float around a lot, especially if you look at a macro environment like a pipeline surrounded by the ocean? How do you estimate, how do you calculate what the OCP would be, and how do you account for the change in the OCP before you design a system?
Well, OCP now, when you already understand CP, it becomes more academic, doesn't it? Because OCP simply means the potential that a structure exhibits when it is not connected to an external load. The idea of the OCP is to understand the concept of corrosion and cathodic protection. So the idea is, if I have open circuit potentials of cathodes, which are say minus 500 millivolts, I have on average, and I have open circuit potentials of the anodic sites, which are say minus 700, then the idea is to polarize all these cathodic sites so that I don't anymore have cathodes or anodes for that matter. So it is more academic. You're not anymore interested in OCP because you want to protect the pipe. If it's a pipeline, you already have criteria. You have criteria from NACE, you have criteria from ISO. You have DIN standards, of course. DIN and EN have now they are under the umbrella of ISO. And for the marine as well, you have both ISO as well as DNV specification. So when you have clearly laid out criteria, which as I said, are actually empirically based, they are not theoretical. So I missed mentioning this earlier, that this criterion of minus 850 millivolts, which is the so-called magic figure for onshore applications, it owes its, the origin of this criterion is that the most active anodic site was found to be about minus 800 millivolts. So you add a margin of safety of 50 millivolts, and they find that over time, using minus 850 millivolts, ably protected all onshore steel structures. So OCP is more of academic interest. When you're trying to protect it, doesn't really matter.
And just one more question. If you have a complex large structure like a ship or a pipe, essentially, how do you ensure that the charge is distributed uniformly?
That's a wonderful question. It will take about 20 minutes to explain in detail. Because as I touched upon it briefly, when you even look at the underground piping in a plant or an industrial plant or a refinery, for instance, we find that the cathode being non-linear itself creates a lot of issues. And so sometimes even the criteria that I mentioned here don't really hold good, or indeed are impractical. So there are other EN standards for that. I didn't go into great detail because it was difficult for me to make this lecture, because I teach routinely and it's very simple. But when you have to encapsulate everything within 45 minutes, it is a tall challenge. So yes, it really depends on the geometry, it depends on the electrolyte, and there are ways and means to design anode systems to take care of this. Because as you rightly pointed out, it is not just the current, you have to now distribute it properly. And not only does it have to be distributed, it is often shielded by other structures. So you have to know what type of anode system to use so that the shielding is minimal, interference is minimal, the gradients are taken care of to the maximum possible extent, and you have sufficient protection.
So these multiple anodes would react as different cells or one large cell?
Well, all the anodes eventually become one large cell together because it's an electrical continuous circuit. No, it depends on the type of system. So you could have a sacrificial system completely, you could have an impressed current system. Typically for all onshore applications during the construction phase, we use sacrificial anodes. But as a long-term cathodic protection system measure, we always rely on impressed current.
I really congratulate you for your wonderful lecture, very lucid manner.
Thank you.
My question is a little bit on a philosophical tone. The anode gets corroded, or it is a sacrifice, right? And cathode is protected. So these days the emphasis of every technology seems to be on sustainability. So is there any work being done or already done, or since it is a chemical industry also in looking at sustainability, electrochemical industry cannot remain back. So I would like to know if there is something being done. Can you please throw some light on that to recover that lost anode? Otherwise zinc will be all gone in protection. I'm just taking it on a different note.
You know, I don't know whether it is a rather difficult question to answer, because the fact of the matter is you need these anodes to protect steel. But picking up on what you said, I'd like to share with you, under the aegis of NACE, of which I'm the trustee, we've embarked on what is known as the impact study, which is International Measures of Prevention, Economics and Application of Corrosion Control Technologies. This was a study conducted in 2002 by NACE with the help of the Federal Highway Administration of the United States. And they found that the cost of corrosion is about 3% of the GDP. 2 years back, this study was reconducted, and in fact we launched it in India as an India-specific impact study, and we found that in the Indian context, the cost of corrosion is about 4.2% of the GDP. It's such a staggering number that even the government of India has taken note of it, and as I was mentioning earlier to some people, that the Ministry of Chemicals and Fertilizers had backed our initiative, and they have announced a Bureau of Corrosion Control in India, because the losses are just enormous. But this is just part of the story. Not only is the cost of corrosion 4.2% of the GDP, 1/3 of this cost can be actually saved by using existing technologies. Now, oil and gas is already taking the necessary measures, but a lot of other sectors, especially water, specifically water, or primarily water, and infrastructure, are doing precious little to take note of this even, because as you know, quality is often lip service. Well, Bureau of Indian Standards has also made an alliance with NACE for corrosion control. GAIL India Limited, which is one of the top gas distribution pipelines, had taken the initiative in 2006 to revise the standard on cathodic protection. I was invited to be a member of that panel in 2006. But I think a lot needs to be done still. And so really it's open communication and ability to share views and implement them. So. That gives food for thought to me. Thank you.
Possibly the last question from you. Yes, yes. I possibly have preempted that I'll be asking this question to you. So I thought, let me be the last. There is an interesting analytical lecture, and I went back the memory lane, and I got that you have the polyethylene tapes cold applied, scores over, fusion bonded epoxy, and the coal tar enamel applied at 5/32 of an inch, which is a hot applied material, which is surprising to me, and it's an eye-opener for me. That's good. But believe me, all of you get a pipe gas. Everybody in Bombay get a pipe gas today. Believe it, you're safe, happy, non-hazardous, thanks to CP. And not his man, the CP. The CP protects the entire pipeline of the Bombay, where you're getting a pipe gas. So, supposing you have petrol and diesel available at Pune, it's a pipeline that goes from refinery to Pune. You have various stations, as he explained, to monitor the corrosion of the pipeline, and the material goes from the refinery to Pune, wherein maybe it is consumed, but earlier it was not so. Now Patal Ganga Reliance, whose raw material goes from the refinery, it's pipeline. So CP is protecting the pipeline, and it is understatement that he says that CP has got a bright future, and since 1970 to today, everybody knows the CP is good, and Mr. Anand explained in a beautiful fashion. The question to you is, we apply fusion bonded epoxy to reinforce bar, which is used under construction of various flyover bridges in the coastal area. Also, you have various tall buildings in the reclaimed area, wherein I see around 5 floors down the level, maybe 6 parking places, 7 parking places, the rebar coating gives away. I know definitely Nace or you or anybody has worked on how to maintain the rebar coating and protect it from rusting. So I'd like you to throw light on that particular thing, because today it is catching up, because there are tall towers, we have a lot of corrosion issues. Over to you, Anand.
This again takes me back to the slide I showed on coating in CP, and I did mention, I recall, that the better the quality of the coating, the greater is the risk of corrosion, and therefore the greater the need for CP. So if you have a rebar which is coated, it absolutely needs cathodic protection. If it doesn't have cathodic protection, you are basically, it's a call to failure of this rebar. If the rebar is not coated at all, there is going to be corrosion, but the corrosion is going to be spread over a much larger area. So the rate at which it's going to fail is going to reduce. The time at which it's going to fail is going to be deferred. That is not to say that the rebar should not be coated, but the point is, if the rebars are coated, they must absolutely, essentially be supplemented with cathodic protection, which is not being done either by the MMRDA or any of the other agencies, which is because of lack of awareness, because of lack of will, because of a lack of attitude to quality.
Thank you.
Thank you.
Thank you, Mr. Anand. So I hope there are no more questions. So we are at the end of today's lecture. So I am here to present formal vote of thanks, and I would like to request Dr. Timmana to present a memento to Shri Anand Kulkarni for his great informative lecture.
Thank you.
And great for our community of coating industry. I thank Anandji once again, and I welcome you to ICT premises. I thank the Honorable Vice Chancellor, ICT Mumbai, for allowing us to use the premises, as well as the Head of the Department of Polymer and Surface Engineering for allowing us to conduct the Color Society activities. I thank Bhumkar family for instituting this lecture series, and I assure on behalf of the society that we will get such kind of speakers, and will keep all the time the whatever ideas of Bhumkar Saab that always bring together management and technology for the societal benefits. Last but not the least, I thank all of you for patience, for attending the lecture, and definitely quite interactive session. Thanks a lot.
They can see a place.